Hello, this is Dr. J back with another episode of my Commander X16 devlog. Last episode, we showed how we can load subsets of images from disk into high RAM and VRAM in order to be able to handle proper sprite sheets. That's a nice start, but there's still a lot more functionality to implement before we can say we have a proper graphics library. Next on the list is something crucial for any sprite-based game engine: animated sprites. Fundamentally, an animated sprite is just a series of images being displayed in sequence. So in order to have an animated sprite, we'll want a bunch of contiguous images in VRAM, and we'll want to point one of our sprite objects to the addresses of these images, one after the other, on a timer. Conceptually, it's not that complicated, but manipulating all the necessary data and memory addresses gets pretty finicky when interacting directly with the hardware. So we're definitely going to want to build out some functions to do most of the dirty work and heavy lifting for us. First, we don't want to just have to hard code all of our sprite data. We could do that, but it will be more convenient for us to design an image metadata format so that we can build data files to import into our program. The first thing we need to do is figure out what data a sprite needs to be able to animate itself. For this purpose, I've ported a simplified version of my Sprite data structure, parsing, and processing functions from the modern version of my exist library into Exist16. My modern one has a bit more functionality than this, but given our resource limitations while programming on retro hardware, I boiled it down to the bare essentials for the Exist16 version. What each sprite needs to know to animate itself is the following: the file name of the file that contains the graphical data for its sprite sheet. To save space, we confine the file name to have a maximum of 4 characters, not counting the file extension. The X and Y offsets of the upper left corner of the sprite, in case we want to fit multiple animations into one sprite sheet. The width and height of each frame of animation. For simplicity, every frame of animation is required to have the same dimensions. The total width of the image, which is necessary to do the addressing math correctly when pulling the frames out of the sprite sheet. The total number of frames of animation in the sprite, the amount of time in 1/60th of a second intervals to display each frame before moving on to the next. Again, for simplicity, we assume every frame is displayed for the same amount of time. If you need to support more complex animations with variable timings, you could essentially define an animation sequence struct that references multiple sprites to be played in sequence. This is an example of something that had somewhat more robust functionality in my modern exist library, but for the sake of saving space, since the amount of space we have to work with is so limited, in this case I decided to just make the assumption that every frame in an animation is on screen for the same period of time. And then we need a bitmask to contain any on-off flags we define. Right now, the only one I have which is relevant right here is a repeats flag that determines if the sprite loops infinitely, or if it only plays once and then stops on the last frame of animation. And then we have a couple more bytes which correspond to bytes 6 and 7 of the sprite metadata object in VRAM, which includes a collision mask, z-depth, horizontal and vertical flip, the sprite's width and height, and palette offset. With this data structure defined, we can then define a format for our game to parse so we can write our sprite metadata into external data files instead of hard coding it. In the past, I've defined custom XML-like file formats for writing my game data, but given the limited resources we have to work with here, we don't have the luxury of being so fancy. So instead, we're just going to encode this information as a raw byte stream that we can read directly into our game without having to do any special parsing. Based on the struct we showed earlier, we can see that our sprite metadata requires 14 bytes per sprite. So the way I'll write and edit the metadata for my sprites is by using a hex editor where I can configure the number of bytes per row, which I'll set to 14 so that each row corresponds to exactly one sprite. Then I can just punch the information directly into the hex editor, and the only thing I need to make sure to keep track of separately is which row index corresponds to which sprite in my game. For example, I might need to remember that row 0 corresponds to an animation for the player's ship, row 1 is a bullet animation, and so on. It's not exactly what you'd call a sophisticated approach, but it is simple and resource efficient, and those are top priorities for us when developing on the X16. If you're not familiar with using hex editors, I think getting familiar with them would be a great idea, for editing the data files that you're likely to make for your games for use with the X16. There's nothing complicated about them. You just put in 1 byte at a time, entering it as raw binary data instead of, for example, entering it as text like you would do with Notepad or another text editor. So, we've defined a file format for our sprite metadata, but we also need to know how to process our sprites as our game is running. That means we'll need to keep track of some information, like our current frame that we're displaying and the value of the frame timer. For this purpose, we defined another struct. We'll have 128 of these, equal to the number of sprite objects in the X16's VRAM, and the two arrays will be synchronized such that the index of a sprite struct in our sprite bank array will always correspond to the same index of the X16's sprite object in VRAM. Then we just need a function to handle our sprite animations. The logic is pretty simple for keeping track of which frame we're on and rolling to the next one on our animation timer, and then looping back to the beginning if it's a repeating sprite. More usefully, this function will also automatically update the sprite object's pointer to the right address in VRAM where the graphical data is located for the frame it's currently displaying. All we have to do is call this function once per game iteration in our main game loop on each of our active sprites, and it will automatically take care of animating them for us. At this point, all the pieces are in place, but there are a lot of moving parts, so it's worth taking a moment to summarize it all. First, we have our metadata file with entries that correspond to the sprite metadata structs in our code. We load these into one of our banks in high RAM so we don't take up any of our precious, extremely limited space in low RAM. Now we have the metadata about our sprites in memory, but we haven't loaded any of the graphical data yet or populated any of the sprite objects in VRAM. Many games are likely to have more graphical data than they can load all at once, so one of the benefits of this approach is it allows us to load our graphics on demand and not have to try to cram everything into memory all at once, only loading the graphics that our game needs at any given time. So, as necessary, we'll parse rows of our sprite metadata, which contain information about which graphical file to load, and then how to split up those graphical files if we loaded a sprite sheet with multiple images. Typically, the raw graphical data gets loaded into high RAM, and then we use the copy high RAM to VRAM partial function that we developed last episode to split the raw graphical data into individual images and copy it into VRAM. Finally, we use our metadata to initialize one of our sprite structs while simultaneously populating the corresponding X16 sprite object in VRAM. Unlike our other metadata, this live array is in low RAM because we need to be able to access it all the time, and its size is relatively limited. Remember that these two arrays are synchronized so that, for example, index 16 in our sprite bank array always corresponds to the 16th sprite object in VRAM. Our sprite struct knows the address of its graphical data in VRAM and the offsets to each of its individual frames of animation. So all we have to do is call process sprite on that index in our sprite bank, and it will take care of all the animation logic for us, including updating the sprite object's pointer to the right address in VRAM to display the graphics for its current frame of animation. All that might seem pretty complicated, and I guess it kind of is, but the whole point of making this graphics library is to take complicated things like this and make them simple to use. So, let's show all this in action, and we'll see that the library functions we built are actually pretty easy to use. Note that I'm going to gloss over the actual implementation details of these functions. We've pretty much already described what they do. For the purposes of using the library, the method signatures are what's important. I will include the source code once I'm ready to release the library, so you can dive into the implementation details then if you're curious. Alright, that was quite a bit of explanation, so let's go ahead and actually see all of these ideas in action. This little demonstration isn't going to be mind-blowing or anything. It's just a simple little demo that proves that all of these concepts come together and work the way we want them to. So, for this demo, all I've done is create a very simple little animated ship. Nothing impressive about this at all. It's just for the purposes of showing that we can animate it. So it's just kind of this little thing with a little animated fire coming out of the back of it. And we have a little one-liner metadata file for how to parse it. So, as you can see, if we bring up our metadata struct to compare it to our file here. First, we've got the file name, and these are just the ASCII codes for the word ship. And if we go into our build folder, we can see that we have a ship.img file. So that's going to be the one that we load the ship from. Then next we have the X offset and the Y offset, which in this case, as we can see, the ship starts at the upper left corner of the image. So the X and Y offset are just both going to be zeros. And then we have the width and the height of the individual frames. And in this case, each frame is 16 by 16 pixels. The entire image is 32 by 32. So the next 2 bytes are each decimal 16, but this is a hex editor, so we put in the hex values, which 16 in decimal is 10 in hex, so 1010 for the next 2 bytes. Then we've got the total width of the image, which is going to be 20 in hex, 32 in decimal. The number of frames is 4, as you can see, simple little 4 frame animation. We set the frame delay to 5 frames, so each 5/60ths of a second it will cycle to the next frame. And then our bit mask, the only thing here is that we have turned on the repeats bit, which is the second bit from the right in the format that I've defined here. And in this case, for the last 3 bytes, it's really the binary representation that we're going to care about, because they're both bit masks where we really care about whether individual bits are on and off. And then the last 2 correspond to bytes 6 and 7 in the Commander X16's built-in sprite metadata in VRAM. And the most important one that we care about here is the bits determining its size, its width and height. And in this case, we've set it to a width and height of 16 pixels in each dimension, since that's the size of each frame. And it's the size of each frame that we care about, not the size of the entire image. All right, and here's where we define our sprite bank, which consists of 128 of these structs. And the reason we set it to 128, again, is because that's the maximum number of sprites that the Commander X16 can support. And then we come to our method signatures. So load sprite is for loading a sprite out of our metadata. So we need the metadata index, which is going to correspond to which row in our metadata file is this. Now in this case, obviously, we only have a single row. So the metadata index for this would be row 0. But in a real game, presumably you'd have a whole lot of rows. And so you just need the index of whichever row it is that you want to parse. Then we have a Boolean. Now, of course, Boolean is not actually a built-in C data type, but I just got tired of typing unsigned car every time I really mean Boolean. So I just defined a, let's see, was it in here? No, it was, here it is. Yes, this is the file where I defined a bool is unsigned car, true is 1, and false is 0. So that when I'm using Boolean logic, I can use these terms instead of unsigned car and 1 and 0. All right, so we have a Boolean which determines if we want to load our sprite into high RAM, an unsigned car, which is the bank of high RAM we want to load it into. This is ignored if 2 high RAM is set to false. And then a Boolean for 2 upper VRAM, which if we're not loading the sprite into high RAM, we're loading it into VRAM instead. And this Boolean determines exactly which address, well, not exactly which address, but it determines if we're loading it into an upper address in VRAM or not, which is necessary for feeding a parameter into the Commander X16's built-in load function. You can see the tutorials that I've mentioned several times, the chapter on files, for more information about this. And then finally, if we're loading it into VRAM, then we also need an unsigned short for the exact VRAM address that we want to load it into. Now, it is important to note that even though this function supplies the ability to load the graphical data directly into VRAM, the vast majority of the time, that's probably not how you're going to use it. I think that more commonly, the way that this function will be used is going to be to load the sprite data into high RAM first. And then, once you've got a bunch of sprite data in high RAM, then on an as necessary basis, you'll load it into VRAM, and that is what the prepare sprite function is for. So this is once again going to take the metadata index, meaning the row in our Sprite metadata file that you need to read from. It's going to take a VRAM address that you are going to write the graphical data to, the high RAM bank that the graphical data is currently stored in, the Sprite index, which corresponds to both our Sprite bank, which contains 128 of these structs, and the array of Sprite objects that the Commander X16 always has at a fixed location in VRAM. Because remember, that built-in X16 Sprite array and our Sprite bank are always going to be synced, so that the index in one is indicating the same sprite as the index in the other. So we use this single sprite index to refer to the position in both. The X and Y position of where we first want to initialize it on screen. And then if there's any particular bits in our bit mask that we want to flip on as we prepare and initialize the sprite, we can add them here. And by far the most common usage for this would be setting the sprite to active right away. And then finally, once you actually need to animate a sprite, once it's all loaded into VRAM and ready to go, you just call process sprite once per iteration of the game loop, pass in the index of the sprite that you want to animate, and that's pretty much all there is to it. So if you had multiple sprites that you wanted to animate, you would just call process sprite with each of the relevant indices in a loop. All right, so let's see how to actually use these functions. As always, we'll turn on 320 by 240 mode. Then we're going to load our sprite meta.dat into the sprite metadata bank in our high RAM. That would be this one right here. Again, for a real game, this would have a whole lot of entries instead of just one for demonstration purposes. Go ahead and enable sprites through the Vera. Then we first call load sprite in order to get the sprite into high RAM by parsing the row for it in our metadata file. So, checking the function signature, the first parameter that we pass in here is going to be the metadata index. Obviously, that's going to be 0 because it's the only index we've got. And then, for the second parameter, it's whether we're going to copy it to high RAM, so we set that to true. And then, for the third parameter, it's which high RAM bank we want to copy it into. So we just copy it to what I have defined as test sprite bank, which in this case is 15. And then whether we're going to copy it to upper VRAM and VRAM address, both of which are values that do not matter because we're copying it into high RAM. So we can just put whatever we want into those. They're not going to be used. But since they're not used, I think it's intuitive to set them to false and 0. We would obviously give them real values if we were actually copying into VRAM instead of high RAM. So that's what's going to load our simple little sprite sheet here into bank 15 in high RAM. Next, we call prepare sprite to copy this sprite sheet from high RAM into VRAM, split up into the proper frames, and initialize the corresponding struct in our sprite bank and the corresponding Commander X16 sprite object in VRAM. So, first parameter here, once again, the metadata index, and that's again going to be 0. The second parameter is which address in VRAM we want to copy the graphical data to. In this case, I'm copying it to what I've defined as VRAM sprite image data, and that's in my exist mem header file. So I'm copying it to 4800 in hex. Obviously, you don't have to use this exact address. You could just use whichever one is appropriate to your game and its memory layout and requirements. And then we have to tell it which high RAM bank we're copying it out of, which is obviously going to be the same one we copied it into with the previous function call. That's going to be the test sprite bank 15. And then we have to give it the sprite index of our of which index we want it to populate in our sprite bank and the Commander X16 sprite objects. So we're going to copy it into 1. An important note, if I remember correctly, I believe sprite 0 corresponds to the graphic for the mouse cursor if you're writing a program that uses the mouse. So unless you intentionally want to overwrite the information for the mouse cursor, then you want to skip index 0 and start from index 1. So we're going ahead and doing that. We're starting at index 1, and then next are the X and Y positions of the sprite's starting position on the screen. I'm setting that to 144 and 160. And then lastly, any bits in our bit mask that we want to turn on as we initialize the sprite. And as I mentioned before, the most common use case for this is going to be if you want the sprite to be active immediately, then you can pass in sprite active, which in this case is a macro defined in the exist sprite header file, corresponding to the first bit from the right in our bit mask. And then the second one is whether the sprite repeats. And the third bit from the right is whether the sprite is finished animating, which will only ever be set to 1 if the sprite doesn't repeat and then it reaches its final frame of animation, then sprite finished gets set to 1. So that's the purpose for that bit flag. Right now, there are only 3 bit flags that I have defined for the sprites, but we have 5 more slots available in our byte here, in our bit mask, if I think of additional flags that should be added to this sprite functionality. All right, so just to summarize, we loaded our sprite metadata that contains all the information about how to parse and load our sprites. Then, using that metadata, we loaded our sprite into high RAM, and then we used prepare sprite to copy the sprite from high RAM into VRAM and set up all of the necessary stuff in the background to make it work properly with the Vera and so on. And then, each iteration of our game loop, we just call process sprite with the sprite index of whichever sprite that we want to animate. And again, if you're animating more than one, then obviously you just call process sprite for each of the sprites that you're animating. All right, so it's just loading the metadata, 2 function calls to get the sprite ready, and then 1 function call to animate it. Not too bad, I think. Fairly easy to use. So let's go ahead and build this project. CD into the build folder, run make, and are you ready to have your socks knocked off? Look at that animating ship, it's so amazing! Sorry, I told you it wasn't going to be a mind-blowing demonstration, but it's actually more exciting than it seems because it proves that all of this works, that it does all of the parsing and loading and then animates the sprite for you with just a handful of function calls. So even though this little example isn't anything too impressive, it's an effective proof of concept that, you know, it wouldn't be that hard to fill the screen with sprites and have all of them animated with a minimum of function calls and just having to define some information in your sprite metadata file. So this is a very nice step towards building out our graphics library to make it relatively simple to add functionality for animated sprites into our game. Just one last thing to note. I have not yet done major performance stress testing with this animated sprite functionality. So I'm not sure how well it would perform if there was a very large number of animated sprites on screen at once. Maybe it would perform just fine, maybe it would be slow. Haven't stress tested it yet. If it does turn out to be slow, then there are some possible solutions for making it better. For example, you might process only 1/4 of the sprites each frame, which would reduce the computational load on the Commander X16's processor by 400%, which is to say it would be 1/4 of the load that it currently is. And the one major change that would need to be made to the functionality would be that each time unit for the animations would become 1/15 of a second instead of 1/60th of a second. But that would be one way to potentially make it much more efficient if it turns out that it's a little slow at the moment. And then another possibility would be to replace the most performance critical parts of the logic with inline assembly. Certainly something that could be done, but I'm hoping that once I use this library to display a bunch of animated sprites on screen at once, that the performance is going to be good enough that I don't have to resort to putting in a bunch of inline assembly, because to be honest, that kind of sounds like a pain. And the whole reason that we're using C is so that we can try to avoid using assembly as much as possible. So that pretty much concludes the demonstration and explanation of the animated sprite functionality for the X16 graphics library. There's still more to go. Next up, we're going to cover our own custom text display routines. And that's also going to take us into talking about tiles a little bit. Up until this point, we've only been messing around with sprites, but the Commander X16 has an entire other aspect of its graphical capabilities in the tile sets, so that's what we're going to start touching on next time. I'll see you then.